Okay, we're going to continue on here, chapter 9, which is solutions. And as we've been talking about, again, solutions are really made up of two parts. There is the solute, which is our smaller part, and our solvent, which is our larger part. And remember, again, a solution really is a homogeneous mixture. So really two things that get mixed together. They typically will have that aqueous symbol next to them in formulas to indicate that it is a mixture. We talked about sort of solubility rules, and we could use the solubility rules as we saw to basically determine when two ions coming together in solution. And that's really where we find ions, by the way, is in solution floating around. If they will come together really and make a precipitate or a solid. And if something is soluble, that means no precipitate formed, and that would get the aqueous symbol. If something is insoluble, that means that we would expect a precipitate to form, and it would get a solid symbol next to it. So we could use those solubility rules to help us determine if you're sort of putting together a couple of ions in solution, would we expect them basically just to still be floating around freely and be soluble, or will come together with some other ion and kind of drop out of solution and become sort of a solid. We talked about the idea again of sort of like dissolves like. And as we talked about, things that basically can use the same sort of intermolecular forces that some other molecule uses will allow them to be soluble in each other and mix. And again, because they're basically using the same type of interaction they use with themselves, they can use with somebody else. So it works really well. It's only when you try to try and cross over different types of interactions, mainly something that is nonpolar, which again uses dispersion forces, and something that is polar that uses either dipole-dipole or hydrogen bonding. Those are very different types of interactions. One is very weak and temporary, which is the dispersion forces. Dipole-dipole and hydrogen bonding are stronger, always ready to go type forces. So ultimately what that means is if you can identify something as being ionic, like an ionic compound, it should be soluble, and again, in something that is polar. Something that is polar should also be soluble in something that is polar. And again, something that is nonpolar will be soluble in something that is nonpolar as well. So these three sort of combinations should always sort of mix with each other. If we're talking sort of like a solid and a liquid, the solid should dissolve. If we're talking about two liquids mixing, they all should look like one sort of liquid together. There'll be no different layers or anything like that. Again, if you cross over polar and non-polar, you're going to have a really tough time. They're going to be pretty much insoluble in each other, and you would not expect mixing to occur. You would expect, for example, maybe different layering to occur if it's two liquids together. Again, because they're using vastly different ways of trying to interact with each other, and they can't maintain that interaction. We then started talking about sort of concentration units, and there was percent mass to mass, which again is the mass of the solute over the mass of the solution times 100%. And remember on this particular one, this is really important because it is, again, the solute plus the solvent. And very often in those type of questions, as we saw, they sort of separate those two values out from each other. So you oftentimes have to kind of add them together to make sure that you actually do get sort of the correct mass of the solution and not just the mass of the solvent. Some other percent sort of concentrations, volume to volume percent, which is our volume of solute over volume of solution times 100%. And we also have percent mass to volume, and that is the mass of the solute divided by the volume of solution times 100%. So remember that if you have any of these sort of percentages, wherever it went there. I feel like I went way too far about right that way. If you have any of those percentages, again, like a 2.5% by mass sodium chloride solution, you can turn that into a conversion factor like we did in a couple of examples and take a dimensional analysis sort of approach. So in this case, since it's mass to mass here, that would mean I have 2.5 grams of sodium chloride and 100 grams of solution. And again, I could use this as a conversion factor flipped around the other way. 100 grams of solution would give me 2.5 grams of sodium chloride. So for any of those sort of percentages, you really, if you are given the percentage, you could use as a conversion factor and take a more dimensional analysis approach, as we talked about, can also help with maybe the rearranging and the math part of the equation just by doing that sort of approach. After we talked about that, I think we finished up on really the most common unit of concentration that you come across, and that is molarity. And molarity is abbreviated with a big M, and it really stands for moles of solute per liter of solution. And we can think of it, as I mentioned last time, as really a formula because it's very common to solve for any one of those three things if you have the other two. So if you want liters, that's going to be moles divided by molarity. And if you want moles, which is a super common conversion, that's going to be liters times molarity. You definitely want to always make sure that your volume's in liters when you're using it with molarity by itself. So if you're just using molarity by itself in sort of a calculation, volume always has to be in liters so it cancels out. And that's because, again, the big M here is moles per liter. So if your other volume is not in liters, it will not cancel out. We also talked about that if you're given something like 2.5 molar sodium chloride and you want to kind of use it in a calculation, definitely a good place to do it as a dimensional analysis type of problem. And you should get rid of the big M. And that would mean in this case, you had 2.5 moles of sodium chloride in a liter. So it's always, again, 1 liter. The number always stays with the moles part for sure. And again, you can use this as a conversion factor. You can flip it around and go the other way there and put the moles on the bottom. That then allows you again to do just sort of opposites cancel. So it's also a really good idea to get rid of the big M when you're doing a calculation. As I mentioned last time, people for some reason when they see the big M, they really don't even sort of think about the volume part of it or where it's at. And very commonly what happens, even if they sort of incorporate volume into the calculation, they will oftentimes kind of multiply when they should be dividing or divide when they should be multiplying. And again, it's because they don't really know where it's at, or a lot of times people just forget about it and just think the M means moles. So again, that is molarity, which has 2 units. And again, by writing it out, you can see it and also take a dimensional analysis approach, which will hopefully keep the math sort of easy. Common conversions that we use with molarity is a lot of times we're given things in grams. So our grams to moles conversion using the molar mass from the periodic table, that is a very common sort of conversion that's used with this. And I would say a lot of times when we do sort of take volume measurements, as you might remember from lab, most of the time you're doing that in milliliters. So milliliters to liters is also a very common conversion that we use a lot in here. And again, a reminder, there's 1,000 milliliters in 1 liter. So that conversion is used a lot in here along with the grams to moles, and also sometimes moles back to grams as well, going in the other direction. Any questions on any of that stuff there? Okay, so I think we finished with that example last time. So let us take a look at this. We're looking for what is the concentration of each of these ions in these 2 separate solutions. So for this solution here, I want to know what is the concentration or molarity of the sodium ions and what is the molarity of the sulfate ions. And separate from that, this solution here, I want to know what is the molarity of the potassium ions and the molarity of the chromate ions there. So why don't you take a moment, I think we talked about this as well last time, and see what you come up with here. Okay, so let's take a look. So in each of these cases, basically you want to think about how it's going to break apart in solutions. So if you had a beaker there and you toss some sodium sulfate in there, it is going to break apart into a couple of sodium ions and a sulfate ion, basically. So basically this guy here would break apart into 2 sodium ions and a sulfate ion there. Now, if we know the concentration of the whole thing, which is 1.2 molar, remember that you basically can kind of do like stoichiometry, so kind of like a mole to mole relationship. And basically, when we look at the whole thing, for every one of these, we actually get 2 sodium ions that's going to float around that solution. How that affects the molarity is we basically just need to take the molarity and times it by 2. And that would get us 2.40 molar would be the concentration of the sodium ions that are basically floating around in that solution. We would do the same thing for the sulfate. It is a 1-to-1 relationship here. And again, because it's a 1-to-1 relationship, we basically would multiply the concentration of the whole thing by 1, which obviously gives us 1 in this case. So this solution would be in terms of not chromate, sulfate here. In terms of sulfate, it would be 1.2 molar. Again, concentrations like molarity are not additive, so obviously they don't equal 1.2. It's more of a proportion. As you can see here, you got twice as much sodium ions as you do basically sulfate ions floating around. So the concentration in that solution of sodium ions is twice as much as it is sulfate. Any questions on that there? That's really the short version of that calculation. The sort of real thing that's happening here, it really is a mole-to-mole relationship like you're doing stoichiometry. So when we look at this molarity of 1.2, that's basically 1.2 moles of sodium sulfate over a liter. And basically what we're doing is really just a mole-to-mole relationship. That's a 1-to-2 relationship, just like we do in stoichiometry. For every 1 mole of the whole thing, we get 2 moles of sodium ions. So that is essentially what we're doing next. We would take 1 mole of the entire thing, will give us 2 moles of sodium. That gets rid of moles of the whole thing and leaves us with 2.40 moles of sodium ion divided by a liter, which is the molarity. Hence why we multiply by 2 in this case. Is the shortcut of that move. But that's really the calculation that's happening. And why we multiply by 2 is really just a mole-to-mole relationship between those two things in terms of how they break apart. And that's how we get there. And it's the same thing if you did the sulfate. You would start with your 1.2 moles of sodium sulfate per liter. And from the equation, again, it's a 1-to-1 relationship between that. So for every 1 mole of the whole thing here, we get 1 mole of just the sulfate ions. And that again is basically this sort of stoichiometry we're going to do here. 1 mole of the whole thing gives us 1 mole of the sulfate. Again, moles of the whole thing cancel, leaves you with 1.2 moles of sulfate per liter, and that is the same thing, obviously, as that answer there. And so is this obviously the same thing as that answer there. So that's really the longer calculation. If you just want to do it kind of quickly and you need the concentration of an ion, that's basically the quick way to do it. Again, if it broke apart into like 1-to-3, you would multiply by 3, 1-to-4, you would multiply by 4, and that's how you could adjust the concentration pretty quickly. Any question on that one there? Now the other one was, I don't remember what was the other one. It was 0.75 potassium chromate. So we'll do kind of the same thing there. Maybe get rid of that part up here. Did there, I think. All right, so if we take our potassium chromate there and we toss it in, again, it's going to break apart into ions because most ionic compounds are strong electrolytes that we talked about, which means they completely break apart when they're in solution and form ions. So that was potassium chromate here. And again, when that breaks apart, we get 2 potassium ions in solution and 1 chromate ion floating around in there. and that was 0.75 molar. Once again, it is a 1 to 2 relationship here, so we would take 2 times 0.75 molar, and that will give us our concentration here of our potassium, which is 1.5 for our potassium. And it is a 1 to 1 relationship between the whole thing and chromate, which means we're basically just going to multiply the chromate by 1 there, or the whole thing by 1. Again for that. And that basically gives us 0.75 molar for our chromate in this case. Same idea, when this goes for a swim, you get twice the amount of potassium as you do chromate. So it's twice as concentrated in potassium than it is in chromate. Any question on those there? All right, the next thing we're going to talk about is dilution. And as we talked about earlier, dilution is really the process where you add more solvent molecules to your solution. In a lot of cases, that is water, since water is a very common solvent. Remember, as we also talked about last time, water is not always the best solvent for things, right? Especially if it's non-polar, it would be a bad solvent. But water, a lot of times, is what we're adding. So we're going to add more solvent to our solution. What that's going to do is make it more diluted and less concentrated. And because we are only adding solvent, the moles of the solute that's in there remains the same, and we're just changing really the amount of solvent. How does that affect the molarity? Well, if we think about molarity, which again is moles of solute, which we don't touch, so it stays the same, divided by liters of solution. Remember, again, solution is two things. It is the solute and the solvent. So when we do a dilution, what we're doing is adding more solvent with mass, which mathematically means we are making this bottom number here bigger. And if we make the bottom number bigger, the molarity goes down. Yeah. You take a small number divided by a large number, you get a small number. So when you do a dilution, what you see is the molarity comes down because, again, you're adding more basically solution. Total volume of solution is getting larger, and that will lower the molarity. Now, there is actually a formula that we use to do a dilution calculation, and this is one way you could do a dilution. This is a volumetric flask. Volumetric usually means expensive, and it usually also means there's usually just one marking on it right about there, for example. And that is the actual volume of the flask. So in this case, it would be like 500 milliliters. And you put a little bit of water in there, you put a little bit of your more concentrated solution in there, and then you basically fill it up with some water. Give it a mixy, shaky, maybe not so much shaky, but some mixy. And then you will have a more diluted solution. As you see, it's a little lighter green in that color than the original, more concentrated solution is. Now, to calculate a dilution, we typically will use M1 V1 equals M2 times V2. So M1 V1 equals M2 V2. This is usually the more concentrated solution. Doesn't necessarily have to be, but usually it is. More concentrated. This is the more dilute solution that you're making. M here is molarity, and V is obviously volume in this case. So you can, if you use this equation, this is the one place where if you are absolutely using this equation here, you can actually leave the volume in milliliters. It will work out okay. If you want to convert it to liters, you can, but you don't necessarily have to. And the reason for that is, for example, if I solve for M1, that would be M2 V2 divided by V1, basically bringing this guy down to the other side. And what that means is if this was molarity and I left this in milliliters and I left the bottom in milliliters, the milliliters are going to cancel out and I will be back to molarity. So everything's all good. If I'm solving for V1, That would be M2V2 divided by M1. Again, M would be the units. If I left that in milliliters and divided it by molarity, the molarities will cancel. The difference here is if you left it in milliliters, you will get your answer in milliliters in this particular case. If you multiply, and I might have mentioned this last time, if you multiply milliliters times molarity, you do not get moles, but you do get what are known as millimoles. And millimoles, if you divide it by milliliters, the millis cancel and you are left with moles per liter. So that's okay. So I would highly recommend, like I said earlier, if you're not doing a dilution equation or dilution problem and using this equation and you're just using molarity by itself, 100% of the time, put the volume in liters. Yeah, so you'll get the right answer that you're looking for. If you are using this equation, you can either leave it in milliliters or you can convert it to liters. It's perfectly fine. The only difference is if you convert to liters, your answer will be in liters, right? If you leave it in milliliters in this formula, you'll get your answer. I would say most people roll with this equation for the dilution because molarity is the most common unit of concentration for solutions. But there is a generic equation that everybody learns these days, or very popular these days. C1V1 equals C2V2. And what C is here is just concentration. It's just a generic concentration. Because technically speaking, if you wanted to use that equation with like percent mass to mass on both sides, it's all good. If you want to use like volume to volume percent on both sides, it's all good. But again, since we commonly use molarity as a most common unit of concentration, M1V1 equals M2V2 is oftentimes kind of used. But a more generic version of that equation is the same equation. Basically, it's just C rather than M. And it works the same way. And you can use other concentrations in there as long as both concentrations are obviously the same on both sides. Also, as long as the volumes here, right, are the same units on both sides. So you can't have one in liters and one in milliliters because it won't work, right? So they got to be the same on both sides. So everything cancels out correctly. Any questions on that there? All right. So let's take a look here at this one here. We want to know what volume of 19 molar sodium hydroxide must be used to prepare 1 liter of a 0.15 molar sodium hydroxide solution. So what's going on in this particular case is essentially we have sitting there on the shelf a lovely drawn bottle here of 19 molar sodium hydroxide, right? So that obviously is more concentrated than the solution we're looking to make, which is this solution, which will have a volume of 1 liter or 1,000 milliliters, right? And a molarity of 0.15 molar. So this concentration is much less, obviously, than this one. So the one on the right there is our more dilute solution. The one we're starting with is actually our more concentrated solution. By the way, there is no chemical reaction happening here because it's just sodium hydroxide and it's still sodium hydroxide at the end. We're just adding some water basically to kind of dilute it down. So we can use this. And like I said before, it doesn't really matter which one you kind of put for which, but usually, again, the more concentrated ones are usually in the ones. So our M1 here would be 19 molar as that's the more concentrated. We do not have a V1, but we do have a V2, which is 1 liter. And we do have a M2, which is our desired molarity of 0.15. So we basically could use our dilution equation, M1 V1 equals M2 V2. In this case, we have all these things. Once again, although they are not technically a fraction, they both are kind of put over 1. And whenever you move something across the equal sign, it always ends up in the opposite location, which means if I want to move this guy to the other side, since it's on top there, it will end up on the bottom on the other side. So it always ends up in the opposite location. And that would give me that V1 is equal to M2 V2 divided by M1. So if I put my numbers in here, We have M2, which is 0.15 molar. We have our V2, which is 1 liters. And we're going to divide it by our M1, which is 19 molar. Here, the molarity on top and bottom will cancel. Because I left this in liters, my answer is going to be in liters, obviously, in this case. If I convert it to milliliters, it would be in milliliters when I would get the answer. But here we have 0.15, and we're going to divide it by 19. And that's going to give us, I'll go this way, that's going to give us 0.007, and we'll call it 90 liters, or a little bit easier unit maybe to use, 7.9 milliliters. Yeah. First off, any question on that calculation? What does that number really mean? That number is our V1, which is basically the amount of sodium hydroxide you're going to take out. So you would go into this beaker here that is the 19 molar solution. You would take out and put into your new beaker. We'll do the milliliters here. 7.9 milliliters of sodium hydroxide, right? Our total volume that we want, right, is 1,000 milliliters. So would I put 1,000 milliliters of water in with it? If I put 1,000 milliliters of water in with it, how much total volume would I have? 1,007.90, which is a little more than I'm looking for, right? So we would not want to put 1,000 milliliters of water in there to dilute it down. We would have to figure out how much water we want to put in there. And typically speaking, if you want to know the volume of water you want to put in there, you can take V2 minus V1, make sure they're in the same units. And V2 in this case is 1,000 milliliters is what we're shooting for, or 1 liter. And we already put in there 7.9 milliliters, which tells us if we take 1,000 minus 7.9, we need to put in there about 992.1 milliliters of water. And that is what we should put in there, 992.1 milliliters of water. That plus the 7.9 I already put in there will give me the total volume that I'm looking for, which is 1,000 milliliters. And now we're not over, right? If I went with 1,000 milliliters of water and 107 total volume, or 1,007 total volume, my molarity would not be what I'm shooting for, right? Because the goal here is to end up with a 0.15 molar. You would put that water in at this point, a little shaky, mixy. And if you do that, you would now have sitting in front of you a solution that has a concentration of 0.15, which is way less concentrated, right, than the 19 molar we started with. And again here, the only thing we added basically was water to dilute it down, increasing the volume of solution, lowering the molarity. So typically speaking, if you solve for V1, that's usually how much of the more concentrated solution you need to take over. If you're solving for V2, that's your total volume of your diluted solution. If you subtract those two volumes, I'll tell you how much solvent or water in a lot of cases that you would need to add to kind of make that solution. Any questions on that there? All right. I tried one, you try one. Here we go. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution? So take a few minutes there, see what you come up with. Okay, let's take a look. So again here, we basically have, we want to make 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution. So basically the two the same things. The only difference is our molarity here is obviously getting smaller. So that should be a hint that this is like a dilution type situation happening. So again, our M1V1 equals M2V2. Once again, basically here we have a more concentrated beaker or bottle that has 5 molar calcium nitrate in it. And since that's the more concentrated one, that would be our M1 in this case. We want to make over here another bottle that is going to have a molarity, which will be our M2 of 0.25 molar, the less concentrated one. And also we will have a V2 here of 500 milliliters. So obviously we do not have a V1, so that is probably what we're looking to solve for. So in this case, again, we're going to send our M1 to the other side, and it'll end up on the bottom by dividing. And that will give us that a V1 is equal to M2 V2 divided by M1. Again, it moves to the opposite side when it goes over there. So in this case, we're going to put in our numbers. And for my M2, it is 0.25 molar. As I mentioned before, if you are using this equation, really this is the only place in most cases. You can leave the volume here in milliliters. So I'm going to do that so you can see how it works out. So I'm going to leave it in milliliters. And I'm going to divide it by our M1, which was 5 molar. Again, because I left it in milliliters, when I divide this, the molarities cancel, and I will be left in milliliters. If you convert it to liters here, which is perfectly fine, the only difference is your answer will end up in liters when it's all said and done. So you just got to be okay, whichever one you do there. So I should pop that in there. I think that's a 25, if I'm not mistaken. So we got like 25 milliliters here of our calcium nitrate. Stop any questions so far on the calculation. Is that my answer in this case? That is not my answer, right? Basically, what that number tells us when we solve for V1 is I'm going to come over to this bottle and I'm going to take out 25 milliliters of that more concentrated solution. Question really wants to know, again, how much water we need to put in there with it. So as I mentioned before, typically speaking, the volume of water will be V2 minus V1. We want to end up with 500 milliliters. We have already put in there 25 milliliters. So was that 475 maybe milliliters of water needs to go in there. So we would add in there 475 milliliters of water. Again, give it a nice little mix. And at that point, we should now be sitting with a solution that has a molarity of 0.25 molar. Question on that there. So you do want to really be careful, make sure you do answer the question, especially with dilution problems. They very commonly will ask maybe a lot of times like how you prepare the solution or how much water that you need. So you want to make sure that you do answer sort of the question that they are asking. And again, they sometimes will ask, how much of the stronger guy you need or what would be the final molarity of a solution if you added water to it. So there are some different things that they do ask for. So just make sure you do answer the question they're looking for. Question on dilutions here. I'm sorry, I hear somebody talking. I don't know where. Over? Oh, there. Thank you. Yes. The answer is 475 milliliters of water because the question really, first sentence there is really, it wants to know how much water you want to add. So again, a lot of times people will just do the calculation and pop down 25 as the answer, right? Which technically would be wrong on this question because it's looking for water. If you want to know how much of your more concentrated solution, 25 would be the answer, right? If you want to know how much you had to take out of that solution. So you do want to make sure, again, you do answer the question correctly. So for this one, the correct answer should be the actual water answer there. Other questions? All right, the next thing we're going to talk about then is some properties of solutions. So the first sort of thing is a semi-permeable membrane. And a semi-permeable membrane allows solvent molecules such as water and very small solute particles to pass through. And a membrane can be anything, like in your cells, you have cell membranes that allow certain things to pass through and other things get kind of stringed out. It could be like a dialysis bag or something like that you'll probably use maybe next week in an experiment. But if you have some type of membrane, although you can't necessarily maybe see it with your naked eye, they essentially have holes in them, right? And they have certain size holes that allow certain size particles to pass through. And then if you got something a little too big, it's going to have obviously a tough time to get fit through the hole and pass through the other side. So it sort of screens things out by size. Colloids are much larger than solute particles in solution. These are large molecules like proteins or groups of molecules or ions that are together. Colloids are homogeneous, which means they do look the same throughout, right? That's kind of what a homogeneous type of thing is. They do not separate and they do not settle out. They are small enough to pass through filters like filter paper. So if you had like a funnel and put some filter paper on it, again, your filter paper, although you can't really see it with your naked eye, has holes in it, which allows certain size molecules basically to pass through. And again, bigger things get caught on the filter paper. So colloids can pass through filters, but they're too large to pass through sort of semi-permeable membranes, so they would get trapped. Suspensions, on the other hand, are heterogeneous, and these are non-uniform mixtures that are heterogeneous, and really sometimes they're large enough that you can see with your naked eye. And they definitely get trapped by filters. They get trapped by semi-permeable membranes. For example, if you threw some sand and water, that would be your suspension there. You threw some sand in there, you could definitely see it. It's a heterogeneous mixture, right? It's not going to mix together. If you try to throw sand through a filter, right, it's going to get caught, right, and not go through. And that's like a suspension. Sometimes you see it in medicine, right? Before you mix it, right? You can kind of see some stuff suspended in there and stuff like that in different layers. So when we look at this, here's our sort of difference here. The circles here are solutions, which kind of float around. Colloids as well float around. Suspensions, again, kind of drop to the bottom. If you have a filter paper and again a filter to try to separate that out, you can see that our solutions and colloids will go through, but again, our suspensions get caught there. And a dialysis bag, again, is going to allow only really smaller things like solution molecules basically to pass through. That brings us to a couple of processes, which is osmosis. And osmosis is the process where solvent molecules will move through a membrane from a lower concentration to a higher concentration in an effort to sort of dilute down the higher concentration. So that's sort of the idea there. So if you had, for example, separated by a membrane here, and you had just regular pure water on one side, and you had some salt water on the other side, the salt water is more concentrated than the pure water because it has stuff dissolved in it. Really, the more stuff you have dissolved in something like water, for example, right, makes it more concentrated and the more stuff that's floating around in there. So what will happen by osmosis is the water, which is less concentrated, will want to shoot over to the saltwater side and pass through the membrane. And it will continue to flow kind of freely until eventually it hits what is known as the osmotic pressure. And the osmotic pressure is basically the atmospheric pressure that's kind of pushing back on it and stopping that flow of water molecules to the other side. And the osmotic pressure of a solution is dependent on how many particles you have basically floating around in there. So the more particles you have in there, the higher the osmotic pressure of that solution would be. Pure water has no osmotic pressure because frankly, it is pure. It has nothing floating around in it, right? So there's no particles floating around in water, just water. And it would have no osmotic pressure. Reverse osmosis, right, is a process where you apply a pressure that is greater than the atmospheric pressure. And what that will do is send the water molecules back the other way, throw some filters there as it goes back the other way, and kind of clean up the water as it pushes back through the other way on that. You could sometimes calculate what is sometimes referred to as osmolarity. And sometimes just abbreviated as osmolarity or osmol. And it's basically calculated with I times the molarity. And what is I? I is really the number of particles that are present. So for example, if you had a sodium chloride solution, it would break apart into a sodium ion and a chloride ion. And that is 1 and 2 particles that would be in that solution for every sodium chloride that went in there. I in this case would equal 2 because there's basically 2 ions, right? If you had calcium chloride, when that goes for a swim, it'll make a calcium ion and 2 chloride ions. And that is 2 and 1 would mean I is equal to 3 in this case. So how does that affect like a solution? So for example, let's just say we had 2.5 molar sodium chloride solution, and we have the exact same molarity here, 2.5 molar calcium chloride solution. So they both have the exact same molarity. The difference here is the number of particles that they break apart into. If we were to calculate the osmolarity of each of these, the osmolarity of this guy would be 2 times 2.5 molar. And again, 2 here is our I value like we got up here from the 2 particles that are present. That would give us for sodium chloride 5 osmolarity, as is sort of osmotic pressure. If I did it for calcium chloride, I is equal to 3 as we did up here. And we would times it by the 2.5 molar in that case. And it's late, so I'm going to grab my calculator so I don't mess it up. So 7.5 osmolarity. The one that has the greater osmotic pressure is the calcium chloride, even though it has the same molarity, and that is because it will provide more particles in that solution. More particles flying around or floating around that solution, the greater the osmotic pressure in this case. So if something breaks apart into a lot of molecules, it would provide a lot more osmotic pressure than something like, for example, water. Water has no ions in it, so I would equal 0, which means it will have an osmotic pressure of 0 in this case. Yeah. Any questions on that there? All right, so let's talk about a few different types of solutions as well, and that is isotonic, hypotonic, and hypertonic solutions. Isotonic solutions exert the same osmotic pressure as body fluids. It is typically the solutions that are used in IVs, because if you're giving somebody an IV, you probably don't want to screw up their osmotic pressure of their cells, because bad things could happen in that case. So what is considered a isotonic solution? It is 0.9% sodium chloride, or saline solution sometimes referred to, or a 5% glucose sugar solution. These are considered isotonic solutions. So what does that mean? What it means is if you take the classic example of a red blood cell and you put it into an isotonic solution, the osmotic pressure on the outside of the cell and inside the cell are the same, which is going to allow basically nice, even flowing in and out of the cell. The cell acts like a semi-permeable membrane, right? So it's going to allow things to come in and come out. And that's a good situation. So things are going to flow nice and evenly in and out of that particular cell. Now, if you make something a hypotonic solution, hypo means lower than, the osmotic pressure inside the cell and outside the cell are no longer the same. And hypo means less than. So what happens is if you take that same red blood cell and you put it into a hypotonic solution, that means outside the cell is less concentrated than inside the cell. So what's going to happen in this case is the process of osmosis, and that's going to mean all these water molecules from outside of the cell are going to go, we need to rush in there to kind of dilute that thing down. That's not so great for your cell because then it's going to feel really bloated, yes, and eventually pop and burst perhaps and cause hemolysis, which is probably not a great thing, I imagine. It doesn't sound so pleasant. So it will cause your cells to kind of burst in that case, again, because you're going to have osmosis bringing all the fluids in. Cells are going to swell and become like a jelly donut and start to pop, right? If you have a hypertonic solution, hyper means more than, and you put your red blood cell into that sort of solution, which is a hypertonic solution. So once again, outside the cell in this case is actually more concentrated than inside the cell. So hyper means more than, so outside is more concentrated than inside, as opposed to here, which it was less concentrated on the outside. And the opposite process is going to occur in this case. Your red blood cell is going to go outside of us is way more concentrated. So it's going to basically just release all his fluids out into the surroundings in an effort to sort of dilute down the surroundings. The result of that for the red blood cell, also not a good thing. It's going to start to shrink and go through what is known as crenation. And as it starts to shrink, because it's basically releasing all of its fluids, and again, not a good situation. That again is why an isotonic solution, that 0.9% and 5% glucose is the important numbers to remember, because that's like your baseline of these are isotonic. It is as simple as, it's, higher or lower than those numbers. We'll tell you again if it's sort of hypertonic, hypotonic, or if it is those numbers, it would be isotonic in this case. Any questions on that there? Let's see here. So here again, some pictures of that in an isotonic solution. We have the classic perfect donut, right? Equal flow in and out. Over here in our hypotonic solution, we're going to swell that cell and make it burst like a jelly donut. And here's our donut hole as our cell starts to shrink, right? As it releases all that liquid, as you can kind of see over here as well. All right. So why don't we do a few here? So let's say we had a red blood cell and we put it in the following solutions. We put it in now we'll go 2% glucose. We'll do 1.1% sodium chloride. We'll do 0.9% sodium chloride. We'll do 10% glucose, and we put it in water. So for each of those, will it shrink? Will it swell? Will it be okay? Will it go through hemolysis or crenation or be okay? All right, let's take a moment for each of those and see what will happen to our pore. Okay, so let's take a look. So remember when you're doing this, the two numbers that are important to remember is 0.9% sodium chloride and 5% glucose. So we'll start up here at 2% glucose. 2 is less than 5. So that's less than, which means this is going to be a hypotonic solution, which would be right about there maybe. And a hypotonic solution outside the cell is going to be less concentrated than inside the cell. It's going to cause everybody to rush into the cell, going to cause it to swell and burst, which is hemolysis, right? Questions on that one there. Over here, 1.1% sodium chloride is larger than 0.9. So that would mean that this is a hypertonic solution. Up there. And that means outside the cell is more concentrated than inside the cell. So it's going to cause everything to rush out of the cell and start to shrink and go through crenation. How about 0.9%? 0.9% is 0.9%. So that would be a isotonic solution. And everybody would be happy in that case, right? So nothing bad is going to happen. We're going to have equal flow inside and outside. We have equal osmotic pressure inside and outside the cell. So it allows everything to flow in and out at an equal rate. 10% glucose is clearly a lot more than 5%. So again, that would be a hypertonic solution. Again, outside is more concentrated inside. It's going to cause everything to rush out of the cell in an effort to dilute it. It's going to cause it to shrink and again go through crenation. Lastly, how about our friend water? That would be what? Good? Yeah, water again has no osmotic pressure, which means it is hypotonic. Yeah. And because it's hypotonic, again, it means outside the cell is going to be less concentrated than inside the cell. And it's going to cause everybody to rush in and start to swell and go through hemolysis, right? Maybe one time where water is not the best thing to use there, right? Not be such a good thing. Any questions on any of those there? Little flow chart from your book there. Dialysis is a process similar to osmosis that allows small solute molecules as well as ions and solvent molecules to pass through, but does retain larger particles like colloids. We do some dialysis there in like a bag, for example, also kidneys and stuff. Do some dialysis to get rid of some waste products. But here in like a dialysis bag here, you can put a bunch of stuff in. And again, it has small holes. It's going to allow certain things to flow outside into the solution. You could do some testing of the solution on the outside to see what was able to flow out. I think this is almost like the experiment next week, maybe. And eventually you'll pop the bag and see what's left inside after so much time and stuff that can't get out. Obviously, larger particles, as we see here, can get trapped inside the bag. Again, it's really kind of size exclusion, even though I can't really see them. There's sort of those holes that are in those bags. Any questions on that there? All right, that wraps up chapter 9. We will go off to chapter 10 for a bit here. All right, so chapter 10, which is good news, bad news, I don't know, we'll see. It's the last general chemistry sort of topic before you could throw your calculators away, yes, and just do organic chemistry for the rest of the semester and not have a calculation to be found. I don't know if that's good or bad or stuff, but don't throw your calculator too far because you'll need it for exam 3 because there'll be some calculations on it. But just to leave you, there's a lot of calculations in this chapter, so we'll talk about some of these calculations here, but it's the last chapter before we head off to organic here. All right, so let's talk a little about acids and bases. Acids have some characteristics. Acids are sour taste. They do cause litmus paper to change color, and oftentimes litmus paper are little pieces of paper, really plant dyes, and basically you can put your solution or tap a drop of your solution on the paper, and it will turn color. And typically speaking, if litmus paper turns, as it says there, red or stays red, it means that that solution is usually acidic. If your litmus paper kind of turns blue or stays blue, it usually means that it's more basic and stuff. So very common in labs. We use litmus paper. It doesn't tell us like the pH of it or anything specific, but it just gives us that idea. This is more acidic. This is basic type of solution we're dealing with. It reacts with metals, as we talked about, in a single replacement reaction. So remember, in sort of single replacement reactions, you got one thing that comes in and kicks out another. And we take some hydrochloric acid here. And basically this guy will come in and kick out the positive hydrogen. That will release hydrogen as hydrogen gas, which you'll see a bunch of bubbles occurring. And the zinc will then hook up with the chloride there and make some zinc chloride. I'll balance it like I'm in chemistry class there and put a 2 in front of that. And again, very commonly, a lot of acids will produce hydrogen gas in these type of reactions where they occur. And that is because whatever is coming in is more reactive than hydrogen, actually. So it's able to kick it out and make basically molecular hydrogen or hydrogen gas. There are strong acids, which are strong electrolytes and good conductors of heat and electricity, or really electricity, not so much heat. I guess a little bit of heat as well. And bases, on the other hand, they have a bitter taste, so don't taste any of these things in lab, obviously. They feel very slippery. A lot of soaps, like drain cleaners and stuff like that, are bases. I think you could still do it. You can still go to Home Depot and buy basically sodium hydroxide to clear your drain, basically. A lot of warning labels on that one, rather than a liquid plumber one, but you can buy that. It also changes litmus paper again to blue as it's basic. Aqueous solutions conduct electricity. Again, we have strong bases, which are strong electrolytes. We also have weak bases, which are weak electrolytes as well. And they are both able to conduct electricity. So let's talk a little bit about acids. And an acid is really a substance that has the ability to produce H plus ions in solution. And when you're dealing with acids and bases, H plus, which is the hydrogen ion, and H3O plus, which is the hydronium ion, are basically the same thing. They basically mean the acid part of the solution. Nowadays, people like to use H3O plus a lot. So I like to use H plus a lot because I don't know, it's what I learned. But they are basically interchangeable. They're interchangeable kind of in formulas. They're also interchangeable a lot of times in reactions. The reason why you might get one over the other has to do with whether or not you include water in your reaction. So for example, this is hydrochloric acid, which is a strong acid and a strong electrolyte. And because it's a strong acid and electrolyte, when you have hydrochloric acid, it will 100% break apart into H plus and Cl minus. And this is the sort of equation that demonstrates basically this process. You dump some HCl into the solution, you get H plus and Cl minus, basically it breaks apart. Now, you get 100% of this, like we talked about with strong electrolytes. You have none of these guys still together in the solution. You could also write this exact same process and include water into the equation. And if you did that, you would have HCl plus water. And a definition we'll talk about in a second is the HCl will send an H plus over to the water in this case. And basically it will make H3O plus when it gains that and Cl minus. And this H3O plus and this H plus are basically the same thing. It's basically meaning the same thing. It is the amount of H plus or acid that's in that solution. The only difference is we get H3O plus when we include water in the reaction. So the short answer is they're pretty much interchangeable. So anywhere I write an H plus, you could just substitute in H3O plus. It's the same deal. Now, there are some strong acids, which are strong electrolytes. They 100% break apart into ions in solution. There's a list of strong acids, which are kind of good to know, I suppose. And here's the list. This is hydrochloric acid. We have HNO3, which is nitric acid. We have H2SO4, which is sulfuric acid. We have HClO4, which is perchloric acid. We have HBr, which is hydrobromic acid. And HI, which is hydroiodic acid. Pretty much this pack of 4 or 6 acids, that's pretty much your strong acid list. Why it's good to kind of know that, not necessarily a lot for us, but it's just a good thing to know because if you come across an acid that's not one of those 6, you could probably safely assume it's a weak acid. So that's just a kind of a process of elimination. So those are strong acids, and that means every one of those, when they are in solution, will not stay together because they're all strong electrolytes. They're just going to completely break apart into ions. So as it says here, if you had a nitric acid here, it will in solution 100% break apart into H plus and nitrate. And this is really why it's considered a strong acid, because if you dump that into a solution here or a beaker, it is just going to break apart into a bunch of H pluses and some nitrates floating around as well. But that is essentially your definition of an acid, which is it is the ability to produce free H plus ions in solution. And that's the key part. That H plus is floating around by itself, or H3O plus is floating around by itself. It's not attached to something. And because these acids here completely break apart, as soon as you toss them into like a beaker, you just generated a bunch of H plus really, really quickly. So there's going to be a lot of H plus freely floating around in that solution, which is why these guys are strong acids and also strong electrolytes because of that. Now, a weak acid will also produce some H plus, but it's not going to produce anywhere near the amount of H plus that something like this would produce. So when this goes for a swim, you got a lot of H plus. If you have like a weak acid, it's just going to produce a little bit of H plus, which is why it's still considered an acid, but it won't produce anywhere near the amount that you will get here. So, and that's why if you add, for example, a strong acid to water, you will see a really big jump in what's known as the pH, because you just added a bunch of H plus in there really quickly. And that's going to cause the pH of that solution to go really more acidic and become very, very acidic. Bases, on the other hand, are really substances that have the ability to produce hydroxide, OH minus for bases. And it's the same idea as acids, except that it is things that have that ability to produce free OH minus in solutions. So being able to produce that free OH minus in solutions is what something is a base. Strong bases or strong electrolytes, pretty much if you look at the periodic table, a lot of our strong bases come from group 1 and group 2 on the periodic table. If you start with lithium and then maybe go to sodium and potassium, make a right-hand turn there to calcium and strontium and barium. If you hook up any of these guys with some hydroxide, you most likely have a strong base. So a lot of strong bases come from group 1 and group 2. As you remember, group 2 and group 1 is the alkali metals, right? Group 2 is the alkaline earth metals. The word alkaline means basic. Yeah, so that is where a lot of our bases come from. Group 1 and group 2 on the periodic table that have hydroxide actually in it. Why are they strong bases? They're strong bases because, frankly, they're carrying the hydroxide with them. Just like our strong acids have the H plus, when they go for a swim, if you jump in some sodium hydroxide into a beaker, it is not going to stay together. It's just going to break apart into free-floating Na pluses and OH minuses. And again, it's the same idea as our strong acids. With a strong base, it will be able to generate a lot of free OH minus in that solution very, very quickly. And that means that it's going to become very, very basic as well. So you will have basically 100% of the ions in that solution and none of these guys in that solution. Now, there are bases that are weak bases that do not actually have hydroxide kind of on them, but they're able to react with something to produce hydroxide. Probably the most common weak base that you will ever come across is ammonia. NH3 is actually a weak base. So ammonia here is a weak base. Most weak bases are actually organic type compounds that have nitrogen in them, like ammonia here. Ammonia, when it reacts with water, will actually accept an H plus from water. And when it does that, weak, right, 2 arrows, like a weak electrolyte, like we saw the other day, it will produce NH4 plus and OH minus. So although it does not carry hydroxide with it, it's able to do a little bit of a reaction with water and produce hydroxide. Once again, though, ammonia will not produce anywhere near the amount of hydroxide as, say, sodium hydroxide if you dump it into the beaker. Because, again, sodium hydroxide doesn't have to go find anybody. It's just going to break apart and release that OH minus. Again, ammonia's got to go find some water, do a little bit of reaction, and it's going to mostly kind of stay together, but produce a little bit of hydroxide. Any questions on that there? Now, when we react a strong acid with a strong base, as we talked about when we were talking about different types of reactions, this falls under the umbrella of double displacement reactions. And remember, one of the reasons a reaction takes place is the formation of water. And that is essentially what you get when you react a strong acid with a strong base. If you take a strong acid and react it with a strong base, you will get two things formed. You will get a salt and you will get water that is formed. Water obviously is H2O. A salt is a fancy word. I'm not sure how fancy it is, but it's a fancy word for an ionic compound. So you'll basically get a positive guy and negative guy together. The water always comes in this case from the H plus comes from the acid, and the OH minus comes from the base. So when you react these two things together, that is how you form water. H plus from the acid, OH minus from the base comes together to form water. The other two things that are left over is where your salt comes from. So for example, if we took some hydrochloric acid, which is a strong acid, and we react with sodium hydroxide, which is a strong base. So we have a strong acid and a strong base. This is ultimately a double displacement reaction, positive, and negative. Remember, in a double displacement reaction, we're just going to switch partners. So that is the deal right there. And again, we will make water. And the water is coming from the H from the acid, the OH from the base is again where our water is coming from. The salt here is going to come from basically what is left over, which is the sodium and the chloride coming together. And that's going to give us basically our salt in this case, which is this guy and this guy. We'll make this guy here. So we get, again, our salt and water in this case. Salt and water here. And again, ultimately what is happening in this reaction is that formation of water, which is why it's taking place. And it's also why, as we talked about, it is called an acid-base neutralization reaction, because basically you're just forming water. So everything is sort of neutralized in that case. Any questions on that there? All right. And there we go. We'll get that. We don't have to worry about that, I think. Here's another example. This is a strong acid, which is nitric acid. This is a strong base. So again, positive, negative, positive, negative. Just like in the previous example, H from the acid, OH minus from the base is going to make our water when they switch. And what's left over is going to make our salt. So in this case, it's K plus, and nitrate, which is -1, will make our salt in this particular case. So again, that is how we get over there to the other side in that particular case. And we do see our salts, which are again just ionic compounds. I would say in most cases the salt will be soluble, so it'll be a solution. I would say probably in most cases that is what you're going to see. So why don't you try one? What is the end result here if we take HBr and react it with potassium hydroxide? What will we get? What's the salt and other product produced there? Why don't you try this one too? H2SO4 and sodium hydroxide. Okay, let's take a look at it since we're getting to the end here. First off, just a reminder that when we talk about an acid, it is like an ionic compound, and the cation or positive guy is always H plus. So if you have an acid, basically your positive ion is always H plus. That is, again, what makes it an acid is the ability to get rid of that H plus, essentially. So remember as well, acid-base reactions are double displacement reactions, which basically just means, right, positive, negative, right, positive, negative. We're going to switch partners. So As we know here, this is basically H plus and Br minus, or the two ions basically that make up that hydrobromic acid. Potassium hydroxide, K plus, and OH minus. So remember that as we just talked about, that is basically where our water is going to come from, right? When those two guys switch. So we should get water here. And now our salt's going to come from these two guys. And again, we want to put it together like we're doing nomenclature to equal 0, right? So in this case, we have +1 and -1, which means we really just need one of each of those. And this would be, again, our water and our salt that is produced in this case. Any questions on that one there? Bottom one, same deal. Positive, negative, positive, negative. Basic unit of this guy, again, is H plus, right? Basic unit of this is sulfate, right? That's why, right, we actually have two of those guys, right, to balance out the charge to 0. Here, this is going to be a sodium ion and a hydroxide ion. Once again, we're going to swap partners. So we're going to get our water formed like this. And we're going to put these guys together. Now, when we put these guys together, it's +1 for the sodium, -2 for the sulfate, which means I need not one of these guys, but I actually need two of those guys and one sulfate here to give me my proper water and salt. In addition, I also need to make sure this equation is balanced, which it is not in this case, yeah? So you need like a 2 there and perhaps a 2 there to balance it. Top one was balanced, so that's also something you want to make sure you keep an eye out on as well. Any questions on that there?